Wofgang Bangerth for the Department of Mathematics at Texas A&M. Professor Bangerth obtained his Ph.D. at the University of Heidelberg. Upon graduating, he worked at ETH Zurich and as a postdoctoral fellow at the University of Texas at Austin. His Dealto library has won several computing industry awards, including the J.H. Wilkinson Prize for Numerical Software in 2007. Professor Bangerth is part of the team implementing the new aspect mantle convection code that uses modern numerical methods and builds on a set of existing high-quality software libraries, such as his own Dealto. Today, Professor Bangerth will focus on the motivation for and usage of these existing libraries, including Dealto. This should be considered part one of a two-part webinar series, in which next month, Timo Heister will focus on the application of Dealto to aspect.
Let's say, the kind of problems that we want to solve in the geosciences, and they're very representative of the overall classes of partial differential equations. I think by and large we can say that the equations that we want to solve in the geosciences, the most challenging ones among those are certainly all PDEs. And that falls into the area that my work is in, with the software that I write. And so that's sort of the backdrop of, let's say, where my expertise lies. And I want to give you a little bit of an overview of what are the tools that are out there that can solve these sort of things. So just to give you a brief overview of, let's say, how I see solving PDEs. By and large, there are three standard tools for this. Right? There's the finite element method, there's finite volumes, and finite differences. And while people prefer one over the other, oftentimes you can actually see them just as variants of one another. So by and large, the workflow for all three of these methods works roughly the same. Namely, you have some sort of volume that you want to solve the PDE in. And so the first step would always be that you replace this volume by a mesh, say a finite element mesh or a finite volume mesh. So on the right, you see a prototypical example of such a mesh. Of course, in reality, these meshes are often much, much more complicated. So here's a mesh that was created, for example, to simulate Yucca Mountain, the nuclear waste repository site, or let's say the proposed nuclear waste repository site. So these meshes are often very complicated, have tens of thousands, hundreds of thousands, sometimes hundreds of millions of cells. Once you have such a mesh, the second step in any one of these three equations is that you define balance relations. So that means, for example, think of a flow problem. For every cell, you would have to write down the equations that relate how much flows into the cell and how much flows out of the cell. Or in statics, you would have to define the stress and the deformation within this cell and how that relates to the stress and the deformation of the neighboring cells. So when you write down these balance relations, they give you a system of equations for the values on this cell relating to the values on the neighboring cell, so you always come out with a typically very large linear or nonlinear system. And the three methods that I list here, the finite element, finite volume, and finite difference methods, really only differ in how do you define these balance relations on every cell compared to the neighboring cells. But ultimately, they come out at the same thing, namely a large linear or nonlinear system, and they all are based on subdividing your domain into small volumes, that's into cells. Now, every code that solves a PDE has to implement these steps. Every code that solves a PDE has to have some sort of representation of a mesh, has to have some sort of representation of these balance relations, and has to have some sort of representation of the linear system or the nonlinear system that we want to solve together with the solvers to actually come up with the solution of these linear systems. And so if you think about, let's say, if you were to write a new code in this general area, or let's say for your particular application, you might wonder, well, I have only so much time in a day to actually address all of these problems. I mean, all of these are, if you want to do it right, projects that would take you multiple years. So how can you do this? And of course, a related question to this is that typically the people who want to solve a PDE are specialists in this particular area. So let's say if you're a geodynamo person, then you want to solve the geodynamo equations, then you know a lot of the physics, but maybe you're not an expert in the numerical methods. So how do we square these sort of things, that the people who are interested in solving an equation typically are not experts in the numerics of solving this equation? They're experts in the physics this equation models. And so I think this is a contradiction that a lot of us have felt over the years, that we need to write codes to understand the physics behind something, but writing codes is not really our forte. Now, in addition to this, I think we all recognize that we don't just want to have the most simple algorithm for every single one of these steps. So the simplest mesh, for example, would be just subdivide a cube into smaller cubes and solve, let's say, a linear system using Gauss elimination, or maybe through Richardson iteration, or any of these simple methods. But I think we all realize that we want to do much better than this. Right, that we want to use state-of-the-art methods for every single one of the steps that are involved in solving PDEs. And here's just a short list of things that one might want to have. For example, we might want to have adaptive meshes. That means we want to have the mesh be fine in regions where something's going on, and to have it coarse in regions of our domain where nothing is happening. Right? Then we certainly want to have realistic, complex geometries. So one of the codes that I'm writing is Aspect, this Metal Dynamics code, and so one of the things that you could do as a simple geometry is just a spherical shell, but of course in reality you would actually want to have a geometry that resembles, for example, the geoid, or maybe that even has surface topography. So it's not enough anymore in that case to work just with spherical coordinates, but you really have to work a little bit harder. Then we know today that if you use just the lowest order finite elements, for example, or the lowest order finite difference stencils, that might give you a solution, but that solution is not very accurate. And we know that if you use higher order methods, that you can get a much more accurate solution in the same amount of time for the same computational effort. So you would want to use, for example, quadratic finite elements, or even higher order elements. Now, that gives you a linear system, and so in order to solve the linear system, you would want to use something like multigrid. and you would want to use something that scales to maybe a few thousand processors, that certainly makes efficient use of current hardware. So for example, most of the clusters, in fact most of the computers that we work on today have multiple processors, and so we would like to use this. Then we would like to use clusters that connect hundreds or thousands of computers. So how do you use this efficiently? And then the final point is that even once you have your solution, you still want to visualize it somehow. And so you want to produce your output in file formats that are suitable for high quality rendering. So you want to use formats that allow, for example, 3D rendering, or just use any of the, let's say, advanced visualization tools that we have today. And so if you see this whole list, I think the question in everybody's mind is, well, how the heck are we going to make this happen in a single piece of code? Most of the codes that we write are written by a few individuals, maybe just by a graduate student. And I mean, it's quite clear that you cannot address all of these points that I have here, all of these 7 points on this list, by a single person. It would take 10 or 20 years to implement all of these sort of things if a single person were to implement all of these methods. So this is essentially the sort of realization that we have come to in computational science, that we somehow have to find ways to write our software in such a way that we can have all of these things, but not have to pay the price of implementing it from scratch every single time. And so the questions that we will have to answer if we go in this direction, if we want to have all of these sort of things, are, for example, do we allow every student to develop their own software? Right? So I'm in a math department, and the traditional mantra in a math department was that every graduate student who's doing numerical analysis will write their own software from scratch. So I think in our department alone, we probably had 50 students who implemented their own Laplace solver. Are we allowing them to do this? Are we requiring them to do this? Or maybe we should switch our approach and say that every graduate student should build on what the previous graduate student did. Or somehow, in some other way, use what others have done before. So that's the first question. The second one is, do we require that we reuse others? And then, well, which part do you actually want to implement? Do you want to implement every method, or do you just want to implement those parts that are specific to the particular application that we want to solve? So in computational science or scientific computing, I think we've come to a conclusion over the last 10 to 15 years that the goal must be to reuse software. And so I think the summary of my talk now on page 11 is essentially that the secret to good scientific software is to use existing libraries, that it just doesn't work in any other way, that we have to reuse what other people have already done. And since this is a talk that is sponsored by CIG, the Computational Infrastructure in Geodynamics, I do want to say that CIG has very much recognized this, of course. All of the new codes that are built by CIG engineers or in collaboration with CIG actually do build extensively on existing software, and I'm going to introduce a few of these packages that other people have used, or that are being used in the CIG software. All right, so to start with, let's say, an overview of the sort of things that are available in the field. Let me just categorize things a little bit. So there are two packages for what we call basic linear algebra. That would mean that you deal with relatively small vectors and matrices, for example, and these packages, BLAS and LAPACK, for example, implement things like the multiplication of a dense matrix with a vector. That is a basic linear algebra subroutine, so that would be something that you find in the BLAS package, or the product between two dense matrices. LabPack, on the other hand, is a package that builds on top of BLAS and that provides, let's say, slightly more sophisticated algorithms based on linear algebra, or based on dense linear algebra, dense matrices and vectors. For example, find me all of the eigenvalues of this thing, or find an LE decomposition, or find the QR decomposition of a matrix. So these are two packages that have been around for a long time. And I'll come back to them later, just like with the other ones on this page. Then, on top of this, there are essentially two very widely used packages called PETSI and TreeLinos that deal with sparse matrices, so with the things that we typically find when we discretize partial differential equations, and with linear solvers like conjugate gradients or GMRES or any of these sort of things. And further on top of PETSI and TreeLinos, you find packages that deal with the finite element discretization, so things that deal with the meshes, the finite element shape functions, and so on and so forth. And I just picked out three of these libraries. That is Dealto, that is my own project that I'm going to talk about some more later on, and two others that are fairly widely used are called LibMesh and Phoenix. There are probably a dozen or 24 others that you can find on the internet that are supported to various degrees and that are used to various degrees. So I don't want this list to be exclusive, but these are, I would say, the three big ones. Now, before I'm going to talk about the specifics of these packages, I do want to come back to the question of why would we actually want to use existing software? Because whenever we talk to people from fields where this isn't so normal yet, so in many disciplines, people still develop their own software. And so when we talk to these sort of people, there are a certain number of arguments that are always being made about why they write their own software. And I think some of these arguments are valid and some are not so much, but I would like to go through them because I think that the arguments against the arguments that they find, the reasons against these arguments, are actually very illustrative for explaining why we build these sort of software packages. So let me look at reason number one. So one of the things that we often hear, for example, is that, I write my own software because it would take me a long time to learn a software package, like PETSI, for example. I would have to understand how it works. I would have to understand its conventions. I would have to read the documentation, and so on and so forth. And that people think that they'll be faster if they write it themselves. And I think that there's some truth to that first part. Yes, you do have to learn a new piece of software, and it's probably going to be painful for a little while. But I think that by and large, it is not true that you would be faster writing your own code. And the reason for this is that these packages are huge, right? PETSI has, I think, 500,000 lines of code. TreeLinos has 1.5 million. Dealto has about 600,000 lines of code. So there is a lot of functionality in these packages. And while it might take you a little while to understand how this all works together, once you get the knack of it, it actually becomes so much easier to build things. And I think the perfect analogy of this is if you think about how you or your graduate students today use MATLAB. Right? They can very quickly throw together a program where, with just a single line of code, you invert a matrix or you form a QR decomposition, and with another single line of code, you solve an ODE, and so on and so forth. So there are all of these tools that allow you to very quickly build something that is fairly complicated, that really allows you to focus on the sort of thing that you really want to do, namely the application. And you don't have to worry so much about, well, how do I actually multiply a sparse matrix with a vector? Right? You have to implement this sort of stuff if you want to do it yourself. So I think if I look at how students today use MATLAB, it's a really good illustration why these sort of packages are useful, because they provide you with things that you can put quickly together once you understand how it actually works. So once you understand a little bit how MATLAB works, and let's say how to write code in MATLAB, you can very quickly actually build something fairly complicated. And so I want to illustrate this in a graph. Namely, if you look at, let's say, the productivity or the progress over time in a project. So if you write code yourself, you can start immediately. I mean, you sort of have in mind what sort of algorithm you want to have, and you sit down and you start writing code, and you make progress from the beginning. But that progress will be at a constant rate, right? Namely, your own productivity. So I would say that the slope of this of these lines is productivity. So you make steady progress. Whereas if you use existing software, if you build something on Ph.D. or on Trilinos or on Dealto, then of course you will have to spend probably a not insignificant amount of time in the beginning to try to read through the documentation and understand how they do things and so on and so forth. So in the beginning your progress will not be very fast. But then once you understand how it all works together, once you've read through the first few tutorial programs, for example, you will get to a point where suddenly it clicks, and suddenly you can start plugging things together, and you realize that, oh, okay, this is how a triangulation works, so let's use this triangulation class. And then immediately you have a very complicated geometry, because that's what this class can already do, and you have an adaptive mesh, and so on and so forth. So from that point on, your progress will be much more rapid. Now, the question, of course, whether that's worth it or not, depends on where that crossover point is, right? So if it takes you 3 years to learn a package, and then you spend the 4th year being productive, then maybe that's not worth it, because the blue line will never cross within the time horizon that you have over the red line. But the experience that I have and that others have is that in reality the sort of crossover point happens after somewhere between 2 and 4 weeks. So I've taught courses on Dealto many times, and other people have taught courses on Ph.D. and on Trilinos, and I think that's sort of our common observation, that it takes students actually not that long to understand how it all works. And so after 2 or 4 weeks, that's when they have a project together that actually can solve something realistic already, that is further along than where they would be if they started from scratch. Now, if you take into account that a Ph.D. takes, let's say, 3 to 4 years, and I think the time of a Ph.D. is more or less the time of the projects that we typically deal with, then the picture that you get is roughly like the one that I have on this page, right, where the crossover happens somewhere at the bottom left. And then the actual gain that you have exists for, let's say, 3 years minus 4 weeks. So you make a lot more progress this way than if you had written everything from scratch. Even though in the beginning it's a little bit more painful, after a relatively short time you actually gain something from it. So just to illustrate that point, when we have graduate students here in my department, they typically used to have, let's say, at the end of their Ph.D. time, a program that could solve, for example, the Laplace equation in 2D with linear elements plus whatever they were working on. So let's say they were investigating multigrid solvers, then their solver had the multigrid component, and they investigated with their software what they wanted to do for their research, but it would still be the Laplace equation on the unit square. On the other hand, so since we started using widely used software, I think it is realistic that our students develop numerical methods with codes that work in 2D and 3D, that work in complex geometries, that have higher order finite element methods, that have, for example, the multigrid solver or preconditioner, and that solve nonlinear and time-dependent problems. So this is what we see that our students can do today, because we switched from implementing it themselves to using widely used projects. And so I think if you added all of these sort of things up, if the students would have to write this from scratch, then that would cost them on the order of 10 or more years to implement this. But because it's already there, and because you only have to plug it together like you write your little MATLAB scripts, these are the sort of things that are quite well within what a graduate student can do as part of their PhD time here. So the second sort of reason that I often hear is that we actually want to understand the methods that we implement, right? And without a question, there is value to actually implement it once. So, I mean, yes, you can read about all of these sort of things in the numerical recipes book, for example. But I think unless you actually implement it once yourself, you will still have only an incomplete understanding of this. And so I hear a lot of people say that they prefer to implement it themselves because then they finally understand how it works. And so as I say, I understand that argument, that there certainly is value to that. But I think this argument goes only so far. So for example, once you've implemented quadrature in 2D, there's no real gain in knowledge or understanding if you have to do it again in 3D. And there's no knowledge in understanding how to do it if you find out that your 2x2 Gauss formula is not enough and you have to do it again in 3x3. And the same thing is probably true if you want to go from linear to quadratic finite elements. So just because you know how to implement the linear shape functions doesn't make it any less painful to implement the quadratic shape functions. But that's primarily work. It's not that you gain much insight this way. And so I think my answer to this is, well, then write your own toy code and get your hands wet with this and dirty and find all of the places that you think you didn't quite understand and implement them, but then after 3 months throw it away. And now that you understand how to do it, you can start building a code on existing software that very quickly will be able to do the sort of things that you've done in these first 3 months, but that takes away the pain of having to implement everything yourself, right? So as I say, I understand the value of doing it yourself, but I think that's something that only goes so far. We really don't need to reinvent the wheel multiple times. The third reason that I hear is, so let's say you build your own code, and when you do this, then you sort of know where the problems are, right? You know if there are bugs. If there are bugs, you fix them, and so you have sort of trust in your own codes. Whereas if you use somebody else's code, let's say if you use Petsy or Trillinos, how am I supposed to know that this code doesn't have bugs? So what would instill trust in me that I can use this software without running into problems, let's say, where it computes the wrong solution and I don't know, right? So this is one of the most often heard arguments that I get. How can I trust other people's software? And I think my answer to this is the following. So the first part of this, you can't be serious to think that your own software has no bugs. I think if we have learned anything in software engineering is that every software has bugs. There's no question about it. My software has bugs, your software has bugs, everybody's software has bugs. As a matter of fact, there's a rule of thumb that there is a bug every 100 lines of code. So there are lots of bugs around in everybody's code. And I think it would be hubris to say that your code doesn't, right? Now, the question is just, let's say, what is your attitude towards testing software? So how do you actually find bugs? And I think that's where these packages that I'm talking about, or that I will talk about some more in the future, that these packages are written by people who have a very professional attitude about bugs and fixing bugs and so on and so forth. These packages are written by people who've done this for decades sometimes. And one of the things we have learned in our field is, for example, that you cannot prevent bugs unless you have extensive test suites. So just to give you an example of my own package, Dealto, we have a version control system where every single change that we do goes into. So I can go back in time 15 years ago, and I can see what exactly the state of Dealto was at the time. Now, every time somebody changes something in the software, we run a test suite that has on the order of 2,700 tests. So these tests take on the order of 10 CPU hours to run, and they're designed to test as much of Dealto as possible. So if I check something in, if I change something in Dealto, and it has some sort of unintended consequence, chances are that one or the other of these tests will fail. And we have websites that actually show us this, that would for every single revision they show which tests succeeded and which failed. And so if somebody changes something in the library that broke something, we will know within the next 2 hours. So what I want to say with this whole thing is that, of course, trust must be earned. There's no question about it. But that the packages that we're talking about here have very professional approaches to ensuring that there are as few as possible bugs in their software. And I think what you will find if you use them is that you do occasionally find something that doesn't work, or that produces a segmentation fault. But it is actually very, very rare that it happens. So I want to claim that most of the packages that I'm going to introduce later have far fewer bugs than the code any one of us would write by themselves. So the argument that you can't trust what other people have done might be true if you take any random code that you download from the internet. I don't think that it's true for the high-quality software packages that exist in scientific computing today. Okay, so from here, I would like to essentially introduce 3 of the biggest packages that exist out on the internet that people use for solving partial differential equations, or let's say solving computational science problems in general. So I would like to give, let's say, a little bit of a top-level overview of this first. So over the last 25 years, there have been a lot of developments in advanced numerical methods. For example, we have learned how to use adaptive mesh refinement. That means that, for example, you start with a mesh that is relatively coarse, and you solve on this mesh, and you come up with some sort of solution on it, and then you look at the solution and you say, oh, there's something going on at the top right. So you make the mesh finer over there. But then at the bottom left, there's nothing much happening, so you make the mesh coarser over there. This is what we call adaptive mesh refinement, often abbreviated as AMR. So I think we understand fairly well how to do this today. Then we have algebraic and geometric multigrid solvers for the linear systems that we need to solve. We have higher order discretizations, and we understand much better today than 25 or 30 years ago what makes the discretization stable. So for example, we know that if you just use the linear elements for the Stokes equation for both the velocity and for the pressure, that you don't get a solution. That what this converges to is not the solution of the Stokes equation, but that you have to do something. So let's say you have to introduce artificial compressibility, or you have to use different finite elements for the velocity than for the pressure. So I think we understand a lot better how to find what we call stable discretizations for equations. We have, of course, today much better ways of parallelizing codes. So you can find quite a number of codes today that solve PDEs, let's say, on 1,000 or 10,000 processors. And if you think of many of the problems in geodynamics, that's, of course, exactly what we need, right? You have 3-dimensional problems that often have heterogeneities on very small length scales. So we need meshes that have 100 million cells, maybe 1 billion cells. And so if you want to solve problems on this scale, you have to parallelize. There is absolutely no other way around it. And then I think we know much better how to solve problems, both linear and nonlinear problems. So let's say if you had the Boussinesq approximation for mantle convection, I think we know today reasonably well how to solve these sort of equations. We know how to solve, let's say, elastoplastic problems and so on and so forth. So there's been a lot of progress in computational science. At the same time, very little of this has actually gotten into applications code. That's not a problem that's specific to geodynamics. This is a problem that I see everywhere in many different disciplines, that the methods that we've developed in mathematics haven't really found their way into the applications. And I think that's one of the other reasons why we believe that these packages that we develop are so useful, because we can implement these sort of things as mathematicians, but then give them to people who don't have, let's say, the mathematical background to implement these sort of things themselves, or to, let's say, understand the details of it, and just give them to them as a black box and make it work there. So let me skip this one for time here. So the packages that I'm going to talk about, this is something that started back in the 1980s. Back in the 80s, people realized that everybody was implementing their own dense matrix vector operations, for example, and that there really is no need to do this over and over again. And so they came up with something that they called the basic linear algebra subroutines. So this was a collection of functions that are written in Fortran that by and large are independent of each other, and that were meant for dense matrix vector operations. Later there was a BLAS3 that also dealt with dense matrix operations. So for example, the product of two matrices, or the product of a matrix and its transpose, and so on and so forth. And based on this, in the mid-90s, there was a package, and it still exists today, it's called LAPAC, that builds on BLAS, and that computes more complicated things. For example, eigenvalues of matrices, or LU and QR decompositions of matrices. So these are, let's say, higher level algorithms, but they still were meant only for dense matrices. And neither BLAS and LAPAC were intended to be comprehensive. So I think the people who wrote BLAS and LAPAC fully understood that these are just building blocks. So that, for example, if you wanted to build your own ODE solver, that you could build on them, and that they would take over the routine tasks, but they weren't meant to actually support one particular application, for example. From today's viewpoint, both BLAS and LAPAC are a little bit archaic. They are written in procedural style and in Fortran 77. There have been later versions that are written in C, but by and large, I think today we would consider these interfaces to be cumbersome. But they still have the purpose, because we can build something at an even higher level on top of BLAS and LAPAC. And so the next kind of package that came along was called PETSI. I think it was called the Portable Extensible Toolkit for Scientific Computing. And it is a package that comes out of Argonne National Labs that was supposed in the beginning to provide sparse linear algebra. So the typical operations that we need to do for PDE solvers, right? So it provides the matrices and the vectors for sparse linear algebra. It has a lot of different solvers, and in particular it does this in parallel. So it runs on MPI, and PETSI is one of those packages that is used on practically every supercomputer up to the very biggest one. So it scales to hundreds of thousands of processors. Now, PETSI was the first package that was really supposed to be comprehensive. It's very large, many hundred thousands of lines of code. So it was supposed to be comprehensive in the sense that every possible operation that you could do with sparse linear algebra in parallel was supposed to be represented in this library. So it is meant so that everyone who has to solve linear systems would be served by this. In the meantime, so in these almost 20 years that it exists now, it has grown into many other directions. So PETSI today has nonlinear solvers, and it has eigenvalue solvers, and has interfaces to every single package you can think in the world. So it's grown in many other directions, but I think the thing that PETSI still stands out for is the comprehensive support for large parallel computations with sparse linear algebra. And so if you want to find it on the web, it has sort of an obscure address. You'd think that petsy.org was taken, but that's not true. You actually have to surf over to the Argonne National Lab, so anl.gov/petsy. And if you Google for it, it's the first hit as well. Sometime later, in the mid-2000s, so Argonne National Lab is, of course, a laboratory funded by the Department of Energy, of which there are many. And the big competitor to Argonne is Sandia National Labs in New Mexico, in Albuquerque. And my interpretation is always that they have a friendly competition going on. And so since Argonne had PETSI, Sandia needed something else. And so they came up with a package that's called Trilinos. And Trilinos originally did similar things as PETSI, except that it was written, I don't know, 5 or 8 or 10 years later. And so it's written in a much more modern software methodology. It's written in C++, for example. It's written as independent packages that you can use independently. So it's much more modular, for example, than PETSI is. Trilinos 2 has grown into many different other directions, just like PETSI, but it is even broader. So for example, Trilinos doesn't just have linear and nonlinear solvers, it also has, of course, eigenvalues, but then it has things like automatic differentiation, and it has uncertainty quantification, and you can come up with practically anything in computational science that would be represented in Trilinos. And as a matter of fact, so Trilinos is intended to be the basis for every computational need that Sandia has. So I personally am a big fan of Trilinos because I like the C++ style more than the PETSI style, but both of them are very high quality packages, and I think as far as functionality, say basic functionality is concerned, PETSI and Trilinos are by and large equivalent. The thing that I want to talk about for the last few minutes is that, of course, now we need to come back to the finite element part, to PDEs. And so that there is now, since the mid-2000s, a large variety of packages. Only a very small number of them is actually, let's say, widely used. And the package that I want to talk about is called Dealto. That's the one that I and colleagues have written over the last few years. And so Dealto is a package that provides essentially the meshes you need for finite elements, the finite element shape functions and quadrature, the linear algebra. So we have our own linear algebra, but we can also interface to both PETSI and Trilinos, for example, for parallel computations. And it provides practically every tool that you will ever need when you write finite element codes. It's on the web at dealto.org or dealii.org. And so let me briefly run you through the, let's say, the kind of features that we have. So it's on the order of 600,000 lines of C++ code today. It's extensively documented. So we have more than 10,000 pages of HTML documentation. And in particular, it comes with a very extensive tutorial. So there's 45, roughly, programs that start from very simple things to much more complicated PDEs, and shows you how to use the different parts of Dealto. It's fairly widely distributed, so we had on the order of 20,000 downloads in 2011. We know of at least 70 publications in 2011 that used us. This is probably a vast underestimate. Not every publication that uses Dealto we know of. It's used in teaching at a number of universities. The sort of things that it supports are, for example, meshes in 1D, 2D, 3D, fully adaptive. It has interfaces to all the major graphics programs. It has automatic refinement. It has every single finite element you can think of, low and high order. And as I say, it has interfaces to most of the big linear algebra packages. It supports computations on multi-core desktop machines, for example, or laptops, but also clusters up to more than 10,000 processors. It's been used for practically every purpose in the world. I took the time to look through the list of publications that happened between 2008 and 2010, And I don't want to go through this whole list here, but you can find from very standard finite element application to some things that you really didn't expect. For example, people simulate how plant roots grow, or they simulate how statues in Rome decay due to air pollution. So even these sort of things can be simulated with Dealto. One of the codes that we built on Dealto is called Aspect. That's the mantle convection code that we built for CIG. And my colleague Timo Heister is going to talk about this in the next webinar in this series here. So it uses 2D and 3D adaptive meshes, has multi-grid solvers, high order finite elements, is fully parallel up to more than 1,000 processors, and so on and so forth. So here's just one of the pictures that we create with it. Just to give you an idea of, let's say, the level at which these sort of packages, and in this case our own package, is written. So we have on the order of 4 to 6 core developers that spend, I would say, most of their time developing this sort of software. And then there's a whole bunch of people from around the world who contribute to it. So maybe 10 at any given time, but over the past 10 years there's been more than 100 who have contributed. There's, of course, a freely accessible repository for the current development version. There's mailing lists where you can ask questions. As I mentioned, there's about 2,700 tests that we run after every single change to tell us if something breaks existing functionality. And then there's websites that track all the changes, the tests, the builds, and so on and so forth. So we really try very hard to produce something that is high quality. As I mentioned, the website is dealto.org, and so if you want to find more information over there, this is the place to go to. So, to sum this whole thing up, what I hope that I have showed you a little bit is that contrary to what we did maybe 20 years ago, today there are quite a number of very high quality open source software libraries that provide functionality for practically every purpose you can think of in scientific computing, from the linear algebra all the way to parallel finite element methods, for example. And the thing that I really want to stress at the end of this talk is that you should really use these sort of libraries. They make programming so much more productive because you can use things that others have done in the past. They implement state-of-the-art methods that are very complicated, and they have far fewer bugs in code than you would probably write yourself. So I think with this I'll leave it, and the last slide is just an announcement for the next webinar, which will be Timo Heister's webinar on Aspect. Thank you.
So thank you very much, Wofgang, for giving us a great overview of the established libraries, the motivation for libraries. I have the chat window open now, so if anybody has any questions, we do have a few minutes for questions. I see that perhaps Wofgang says he doesn't have the chat feature up, so maybe not everybody sees the chat window. I see Katrina actually, I think, has a question. Katrina, I'm going to enable your audio and let you speak. Katrina, can you, your audio should be enabled. If you turn your mic on, do you have a question? So if anybody else has any questions, let me know. Either raise your hand or make a request. And if not, I want to thank everybody for attending our inaugural webinar, and thank Wofgang once again for his time this morning. Please remember that our next webinar will be on November 8th, the same time. Again, it will be Timo Heister. He'll be talking about aspect. Thank you, everybody.